Welcome to a tutorial on the Bjt Biasing Circuits Part 4, and of course in this particular tutorial video we're gonna learn about the voltage divider bias. Okay, so I'm just gonna pen it down over here. We're gonna learn about the voltage divider bias. Okay, so as I said, that this biasing technique is just a type of modification over the the conventional emitter bias method. And here the entire circuit that gets its name over here is basically due to the modification concerned. So I'll just like to bring the circuit over here. Okay, so here's a circuit. Alright, so as you can see in this particular the circuit of the voltage divider bias, in this particular circuit you can see that, well, we have a collector resistor named as RC, and then we have this emitter resistor RE, and apart from that we have, well, two other resistors in the front part of the circuit forming the biasing network. And as you can see, if you just take a closer look, that, well, here R1, okay, R1 and R2, they form a voltage divider network. Okay, so they just form a voltage, there you go, divider network. Alright, so this particular voltage divider network that's just been formed by R1 and R2, they just help in, well, biasing the input input part of the BJT circuit over here. So they just help in keeping the base terminal biased at a higher voltage than the emitter terminal over here. Okay, so that well, the base emitter junction remains forward biased. Alright, so now this particular voltage divider that we have just, well, included here in order to keep the the base emitter junction forward biased. Now the entire circuit basically gets its name from this particular the voltage divider network formed by R1 and R2 in the the input part of the circuit, and as we can just, well, call this one as, well, the voltage divider biasing method. That's exactly where the name of the circuit basically comes from. Okay, so now in order to couple the input signal into the the circuit over here, we have the capacitor CI, that's the input signal coupling capacitor, and there's an output capacitor that's just known as CO. That's the, well, that's the the output signal decoupling capacitor. It just helps in separating the DC components of the the collector current from the out. It just helps in, well, separating the DC components of the collector to emitter voltage from that of the the output waveform, which we're going to basically obtain from across that of the collector terminal. Okay, so apart from that we have this capacitor that's CE over here. Now CE, this capacitor you haven't come across in the previous in the previous biasing methods other than, well, emitter biasing. So this particular capacitor CE is basically known as the bypass capacitor. Okay, I'm just going to pen it down over here. All right, there you go. So now this particular capacitor, what does it do basically? That's the question. Okay, so whenever just assume this well, a condition where you're just gonna apply an input signal, and then that input signal is gonna create a sort of let's say the input signal, well, it's sinusoidal in nature, and we expect an output which will just be an amplified version of this sinusoidal input signal over here. So now this particular input signal at the base terminal of this BJT, which is of course an NPN type BJT used over here. So it's just going to set up variations in the collector current. All right, and now the variations are always directly proportional to the form of the signal. So since it's a sinusoidal signal, the variations in the collector current would also be sinusoidal. So the main problem that's going to occur over here, as well, the collector current, as you can see, well, it should flow through the collector resistor. There you go, and then it would come out as well, and then we'd have an emitter current, flowing through the emitter resistor. And now, as we know, in this CE mode of the transistor operation, since the emitter current is since it's approximately equal to that of the collector current, their magnitudes are very very equal to each other. I mean their magnitudes are almost equivalent. So in that case, the collector current variations, they're just gonna set up variations in the emitter current also, and that would result in the variation of the voltage, that's the DC voltage, across that of this emitter resistor. And now once that happens, the circuit doesn't remain, I mean the operating point of the circuit, or rather the Q point, as you may also know, call it as. So this Q point of the circuit doesn't remain fixed anymore, and it just varies about where we just wanted to fix it. So in order to just get rid of all such kind of problems, we had to include the the bypass capacitor CE right over here, so that it just bypasses all the AC components of the the collector current across, I mean through itself, so that it doesn't enter in through the emitter resistor over here. So that just helps in improving the circuit stability once more. And now in this particular circuit, what basically happens here is that since it's a modified version of the emitter bias circuit, so here the emitter resistor RE basically helps in improving the stabilization. Okay, so I'm just gonna write it down over here. So this improves stability of the operating point. Okay, stability of Q point. I'll just write it as Q point. Okay, and here the voltage divider network, that's R1 and R2, okay, it just helps in keeping the base emitter junction forward biased. Alright, so having given that bit of introduction, if y'all would take a good look at this particular circuit, then now we have a voltage, okay, developing across that of the resistor R2 over here. Okay, so I'm just gonna call this one. I'm just gonna call this particular voltage that develops at this, the node where the base is in contact with the voltage divider system. I'm just gonna call this voltage level as V2. Okay, so now the V2 voltage level, speaking from the design point of view of this circuit, the V2 voltage level must be higher than that of the voltage level that develops across that of the emitter resistor. Okay, so I might write this down as well. V2 must be greater than that of the emitter voltage. So now the emitter resistor would have a voltage drop across itself given by the product of the emitter current and the emitter resistor's resistance. Okay, so now V2 must be greater than that of the voltage drop occurring across the emitter resistor, and that V2 should be at least be greater than the voltage drop across the emitter resistor by at least the cut-in voltage of a PN junction. So here we have the base emitter junction over here, which is a PN junction. Okay, now the cut-in voltage of a PN junction, if the material, or rather the BJT used over here is a silicon BJT, then in that case the cut-in voltage value is approximately 1.7 volts. Okay, so the V2 voltage should at least be higher than the voltage drop occurring across the emitter resistor by the at least by 0.7 volts. That's the cut-in voltage in order to forward bias the base emitter junction. Okay, so I'm just going to write this down over here. So this is the base emitter voltage. Okay, all right. So now in order to now as we can see over here that this voltage drop, that's V2 occurring across that of the R2 resistor, is required to forward bias this base emitter junction over here. So we can basically calculate the magnitude of V2 if we'd assume that from the power supply, that's VCC, a current, let's say I1, enters in through the voltage divider, and then a part of it goes into the BJT as the base current, and the other part I2 would continue through that of R2, causing the voltage drop V2. But in reality, you don't get any quite precise while measuring such values over here. So we can just approximate this condition by just saying that here I1 is approximately equal to I2. Why so? It's because the value of the base current, that's IB, is, well, it's quite less, sorry there, it's quite less compared to the value of I2. So we can just say that, well, I1 is approximately equal to I2. And now, speaking from this point of view, we can basically obtain the value of I1 through this sort of using conventional methods from that of circuit theory. We can just basically write this down as, well, I1 it will be equal to the VCC divided by that of R1 plus that of R2. We can just write this down over here. And now if we just want to find out the voltage drop V2 over here, we can just, well, multiply the value of I1, which is approximately equal to the value of I2, with the resistor, the resistance of this resistor R2 over here. So I'm just going to multiply that so that we can get, well, V2 is equals to, well, I1 R2. Okay, so that basically gives us VCC R2 divided by that of R1 plus R2. Okay, so here's the voltage drop that's basically, well, keeping the the base emitter junction forward biased in this particular circuit configuration. And now, if we just, well, talk about the stability of the circuit, then well, we need to make a certain change over here in this circuit. So before we do that, let me just tell you, we're basically going to apply the Thevenin's theorem in order to, well, reduce the input biasing network of the circuit to a much more simpler manner, so that it's easier to analyze the circuit over here. So okay, so let's just do it over here. I'm just going to bring up the modified circuit diagram. Okay, so here's the modified version of the original circuit. Okay, and I can see over here that we've eliminated all the capacitors. If you just compare it with the previous diagram over here. Now we just eliminated the capacitors in order to, well, keep it just simple enough, so that since we're dealing with the DC biasing conditions in this particular circuit, so the AC part of the signal fluctuations, well, that won't matter over here. So since we're applying the Thevenin's theorem for the DC analysis and biasing of this particular circuit, so it's against the rules to include the AC parts as well. So that's why we just eliminated the capacitors, and it's further just helps in cutting off the unnecessary complications that it may give rise to. So if you just take a look over here, that the input part has been just, well, reduced to a a circuit that's just given by Thevenin's theorem. It says that you can just, well, reduce any particular network to a voltage source in series with some sort of a resistor. Okay, that represents the internal resistance of the the particular network reduced. So we just did that. So here we have the internal resistance of the network. We just want to well, represent this with the symbol of RT, and here's the Thevenin voltage source. We're just going to represent it over here with VT. Now the question comes, how are we supposed to get the magnitudes of these two quantities? Well, let me just tell you. If you just take a look once again at the network, we're getting a voltage from across that of the R2 resistor in this the voltage divider network formed by R1 and R2. And over here we just reduce this particular network with Thevenin's theorem. So the amount of voltage drop that we're just getting as output, since it's obtained from that of R2, so the voltage drop that's going to occur across R2, that's exactly what we have calculated over here. That's V2. This is going to be our VT. So this is so this particular quantity is the Thevenin's voltage from that network whenever we apply this theorem. So here VT's magnitude is already obtained, and if we're just talking about RT, then if you just take a voltage divider network, as we've seen in the original circuit over there, so that's exactly the voltage divider network that's been included in the original circuit. So in order to apply Thevenin's theorem to this particular network, in order to find the internal resistance of this network, we just need to do what we need to do is basically we're just gonna short the all kinds of voltage sources that are just connected with it. So we have the the power supply voltage, that's VCC connected, so we're just gonna be shorting it. So this goes, and finally we are just gonna short this entire thing. Okay, there you go. And now since our output is just obtained from the junction of that of R1 and R2. So let's just imagine that we're having an input current entering through this particular terminal, and then we have R1 and R2 in parallel. So since the internal resistance over here be given by, well, R1 in parallel to R2, we can just represent this thing by, well, R1 R2 divided by R1 plus that of R2, and this is exactly our Thevenin's resistance RT that we can obtain for this particular circuit. Okay, so using these basic theorems over here, we could just, well, reduce the circuit. And as soon as we've just reduced the circuit, if we just take a look at this input loop containing the Thevenin's voltage Vt, the Thevenin's resistance Rt, the base emitter voltage, and the voltage that develops across that of the emitter resistor, okay, due to the emitter current just flowing in through itself, we can just basically write down an equation which will just basically be the equation of this particular input loop over here. So the equation would look something like this, as I'm writing down over here. So we can just write it as, well, Vt equals to that of we'll have a base current IB entering in through the base terminal of this BJT. So this base current would certainly flow through the the Thevenin's resistance RT. So we're having a voltage drop across the Thevenin's resistance RT. Okay, so that's given by IBRT. Okay, plus that of the base emitter voltage, that's VBE, and also adding together the voltage that develops across that of the emitter resistor, that's given by IERE. And now we also know that for a CE mode circuit, here we have the collector current entering into the BJT, and then we also have the base current entering, and, well, they just together join and leave as the emitter current. So since we have the emitter current equals to, well, IB plus that of IC as the base current plus that of the collector current, so we can just substitute the value of emitter current with this particular value. Okay, so I'm just going to write that down over here. So therefore we have, well, Vt given by, well, IBRT plus that of the base emitter voltage plus, well, IC plus IB in the place of that of IE, that is multiplied with RE to get the final equation which we have over here. So now from this particular equation, if we just, well, try and make the base current as the subject of formula, then we're going to get, well, Vt minus that of VBE, and then we're going to get, well, minus ICRE, okay, and this whole thing, well, divided by that of, let me just see, well, RT plus that of, yeah, IRE. Okay, there you go. So now here we have our required expression where we can just get the value of the base current. So let's call this one as, let's say, equation 1 over here. That's better. Okay, so now apart from that, we also know that all kinds of BJTs, they have a common equation representing their output, linking their output current to the input current. So this equation is represented as, well, IC equals to beta times that of IB plus that of beta plus 1 times that of ICO. And as you'll have seen in the previous tutorials, that we've just represented ICBO as ICO over here, so that's not a problem, in order to, well, generalize the whole thing over here. So now here, this equation that we have over here, this is equation 2, and as soon as we substitute the value of the base current from equation 1 into that of equation 2, we're going to get a value, we're going to get basically an equation that would look just something like this, as I'm writing down over here. Alright, so there's the equation that we were looking for, and this is exactly the one that we require in order to find out the various stability factors of this particular circuit. So we're just going to call this equation as, well, equation 3. And from this, if we just try and find out the various stability factors, let's just do the same over here. So we're going to obtain the stability factor S, which is just, well, the variation of the collector current versus that of the the leakage current, ICO, and that will be, well, given by, I'm just going to write down the expression over here. Now this particular expression of, well, S shows that, well, here we're getting, well, a larger value for that of, we have a larger expression over here. Now this particular expression, if we just, well, get the values for the RT, RE, and the beta over here, then we'll calculate and find out that the value of S is, well, fairly less. And similarly, we can, well, go forward and find the values of that of S dashed, or S dash, well, basically represents the variation of the collector current with respect to the base emitter voltage. Again, it's obtained as well minus beta by that of RT plus beta plus 1 multiplied with RE. So this expression for that of S dash, and finally we can obtain the value of the other, let's change the color over here. So we can just obtain the value of S double dash over here, and that will be given by this large expression over here, where we can see that it's quite large in size, and we can also see that there's a part of this expression of the S double dashed, as we can see over here, that it also contains the expression of S, okay, where it's just given by beta SRE minus that of S ICO. Okay, so these three values of the various stability factors that we have over here, we can just see that all has, I mean all of them over here have, quite larger expressions. I mean expressions larger pertaining to their sizes. Okay, now this basically indicates the fact that over here, if we just go forward and put the values of the respective variables included in the expressions, okay, well, then we can see that we shall obtain fairly smaller values of the stability factors. So we can just plot down the advantages and disadvantages of this particular circuit. So here we go. So in the advantages section, we have, the circuit, as we have seen, that it provides, excellent Q point stability against, all sorts of distortions present. Since the, the values of the various stability factors, as they indicate, we've seen that they have fairly low values. Well, and that's why we also seen over there that, if you just take a look over here, that, the dependence upon the, leakage current is fairly low, is much lower than what we have seen in the previous circuits. So that basically gives us an idea that the circuit is almost immune to thermal instability. Okay, and then we have the least amount of distortion is produced, as I said, due to lower values of the various stability factors, and lower distortion, that means better amplifier performance. And then we can see the disadvantages of this circuit. As you know, a coin has two sides, so that's why the complex design process will actually makes this type of circuit a little much a bit tougher to fabricate. So that's the disadvantage point number one. And then we have in order to basically make the circuit functional, and in order to ensure the proper zero signal current, okay, we need to maintain the circuit at a higher amount of VCC. That means we require a higher power supply voltage in order to maintain the circuit functional. Okay, so that's it from this tutorial for now, and hope you've liked our tutorial and have been able to understand the underlying concepts. So don't forget to catch us on our next tutorials. So till then, it's just gonna be a short goodbye for now, and thanks for watching.